Thank you very much. First of all, I would like to thank Anastasia and Stefano. I think this conference is super nice and I'm very happy to be here. So this is afternoon, so I'll try to be less technical possible. I have a lot of pictures. I will also draw some pictures. And since we heard a lot about elasticity and so on, I will also be sloppy on all the things that were already said during the talks of this morning, yesterday, and now. Thanks to Daniel, I should have updated my slides if I would have knew what you were talking about. But yeah, actually, I'm going to present a recent paper that I have with, a recent couple of papers actually, that I have with Daniel and Aapo. Let's say, I will tell you more precisely what are like the meaning of this area strict thing that you read here that maybe is known to everyone, but maybe not. But before going there, I would like to give you some motivations for why we ended up studying this class. And as you can imagine, the motivations come from nonlinear elasticity. But I'm not at all expert about this. So I really super summarized some behaviors that were described these days about the theory. And we will see why then it can be interesting to study the closure of some homomorphisms with bounded variation. So the prototype, the classical problem in nonlinear elasticity has been described many times. So I'll go quickly on this. We have two reference configurations, omega and delta, and we can imagine that we have a prescribed way how the boundary of omega is deformed onto the boundary of delta, and we can imagine for this talk that the deformation is on the boundary is super nice. So diffeomorphism, for example. And then we consider all the possible elastic deformations of the interior onto the interior. So elastic is reversible shape change of the material. So we heard it from Barbara at first yesterday that the proper mathematical object to describe this is the notion of homeomorphism because it caps continuity and injectivity, okay? And so among all the possible elastic deformations of omega onto delta which are extending these boundary values, we look for those which are optimal for those for energy functionals of this form, which are the classical ones appearing in applications. And clearly, in order to have some reasonable model, then one has to impose some assumptions on the stored energy density, that is this functional W. And once again, you heard them many times today already. So clearly, the first request you make is the non-interpenetration of the material. And so at least you have to require that your density blows up when you want to self-intersect. So when you're not anymore orientation preserving. And then you want to penalize optimal configurations to have some sort of extreme situations like a too high compression or infinite stretching. So at least you ask the energy to, again, blow up whenever the determinant goes to 0 or when you stretch too much when okay, the deformation stretch to plus infinity, or even if you want the determinant goes to infinity. So again, this is not new, hopefully for you. So the standard prototype, the energy density, as this satisfies these good controls from more or less above and below. So it has some p growth in terms of the gradient of the deformation, and then there is a convex function in general of the determinant that is blowing up when the determinant goes to 0 or to plus infinity. Now, if we call theta p the class of homomorphisms in the corresponding Sobolev space, corresponding to the growth conditions, extending the fixed boundary datum, that the problem becomes, okay, looking for the minimizers, if they exist, of the energy on the class theta p. And as we know, this problem is very different depending on the relation between the regularity P and the dimension N. So when P is bigger or equal than N, actually our energy is lower semi-continuous and coercive in Sobolev. So at least you have a Sobolev minimizer. The point is whether the Sobolev minimizer is injective or not. So if it's an homomorphism or not, and the most important, let's say, the first contribution that kind of gave rise to this theory is the one that's dating back to John Ball. for P strictly bigger than the dimension, then the answer is yes, okay. When P is equal to n, then let's say we heard something also from the previous talk, that in some super nice situation that let's say the answer is not is partial. Let's say there is not a complete view of the P equal to n case, but in some nice situation when good controls also on the boundary, you have to work with mappings of finite distortion, ask for a lot of integrability on the distortion, blah, blah, blah. You still can get some good existence of the homeomorphisms. But when P goes below, so the case we are more interested in today is P below the dimension, then, okay, for sure, you lose the lower semi-continuity of the functional. So, first of all, you have not any more existence of a minimizer in Sobolev via the direct method. So, one can do different things. Like, one option is consider different models, which kind of, anyway, allows for minimizers which are physically reasonable. Like, this is a very non-exhaustive list of literature on this. For example, there are some models from Duvan now and Carlos Mora Corral, also another one with Marco and Oliva, but this is an option. The other option is, we heard it this morning, relax, okay? So try to recover somehow the lower semi-continuity in the relaxation. Well, one possibility, so there are two cases here, no? So when P is strictly bigger than 1, your functional was coercive. So you have to just recover the lower semi-continuity in the relaxation process, so that in that direction, depending on who is the topology you use for the relaxation, you have to understand then who is the new class of competitors, so who will be the closure of the homeomorphisms theta p with respect to the topology that you use for the relaxation. The case P equal to 1, your initial energy lacks also of coercivity. So then in the relaxation, you have also to recover coercivity in some sense. So the only way there, you can't avoid, you have to relax in BV, okay? Then okay, this is what we are more interested about, since we are not good to go on with the existence theorem theory in when P is strictly bigger than 1, then what we do is, okay, let's try to do the easy things in the more difficult case, okay? The first thing that one can have in mind is to relax with respect to the weak start topology in BV. But actually, this is not a good idea if you have in mind the elasticity as an application, because you can produce limits which behave bad with respect to the condition of the non-interpenetration of the material. Let me show you why. So first picture. You can imagine to have a sequence, such a sequence, which is the identity in the gray part, that is mapping the unit square to the unit square. And then the colored rectangle is mapped onto the colored rectangle, and the colors are matching. So you take this yellow rectangle and basically you stretch it more and more and more and more in a thinner and thinner rectangle, let's say layer around the half diameter of the square. So in the limit, what do you obtain? You obtain a mapping, which is the identity almost everywhere, and that is mapping this point, the yellow point on the left, onto the segment, and it's mapping the green segment onto the point, is squeezing there. Okay, so far this sequence says nothing. You have to imagine to take this construction and repeat it while rotating around the center of the square. So what you end up with at the end is a map which is the identity exactly everywhere but in the center, and the center is mapped onto a disk, okay? And then, so if you take now two disjoint sets, one is the center, like a singleton, and this red disk, really disjoint, then the image overlaps completely, like you have a positive measure of overlapping. This is something that you don't want at all as a limit of elastic deformations, okay? So weak star topology for the relaxation is kind of too weak. So one has to come up with relaxations with respect to like less weak topologies in BV. And two good choices, I will tell you then why these are two good choices, are the strict topology and the so-called area strict topology. So strict topology probably is more popular. basically, you say that a sequence in BV is converging strictly to a limit in BV if you have the weak star BV convergence, so Uj is converging to U in L1, and the derivatives of the approximation are converging to the derivative of U in the sense of measures. But on top of that, you ask that the total variation is converging to the total variation. So this is the strict. Area strict asks something more. It says basically that there always exists two other sequences of measures. You can always, decompose the gradient of the approximating sequence as a sum of two measures. And one of them is approximating strongly the absolutely continuous part of the gradient of the derivative, of the limit. And the other one is approximating strictly the singular part. So more or less, you're doing the best you can out of the singular part, out of the singular set, okay? Clearly, by the definition, it's clear that area strict implies a strict. And why the name area? Well, because it's not immediate to see this, but it can be proved pretty easily that requiring the area strict convergence means requiring the convergence of the area functional plus the total variation of the singular part. Okay, so this gives the name. Okay, the other implication is not true. Area strict is stronger in practice than the strict convergence. This is a counterexample. Here you see with step functions, you are approximating to x, even if it's one-dimensional. Then you have strict convergence. It's very easy to check because the total variation is 2 in both for the approximations and the limit. But it's not area strictly converging because the area functional here is would be 1. You are doing just jumps. So plus the total variation 2 gives 3 for every n, while here the limit gives square root of 5 because it just has absolutely continuous part. So why are these two topologies interesting for our talk? Because there are two interesting relaxation results in BV. The first one is from Christensen and Rindler. They study a relaxation of the linear part of the energy. I'm not talking about the determinants. I'm just talking about the part involving the gradients. And they proved that the relaxation in BV with respect to the strict convergence is nice. It's continuous for Dirichlet boundary data. Then there is another result from Bayer, Kromer, and Kruschik, which extends this BV relaxation for more complicated boundary conditions. And then there is another, let's say, refined version of the Christensen-Rindler result made by Rindler and Shaw, where they relax with respect to the area strict topology, and the relaxation is still continuous. Okay, so in this direction, if one wants to sooner or later try to do relaxations on the elasticity problem with p equal 1 in BV, then these are two good options. So in that case, then it becomes interesting to understand who are the new competitors. So who are the closures with respect to the strict or the area strict topology of, this is what I called before theta p with p equal to 1, of theta 1. So we can already say something about this class, these two classes, which are the objects of interest of this talk today. And actually, these two classes coincide with the strict and the area strict closures of the homeomorphisms in BV. Now I'll tell you why. Because, okay, from now on, we will just talk about the planar case, okay? So in the plane, it was already quoted this week by Alexis and Barbara, I guess. There is a super interesting approximation, diffeomorphic approximation result that says that any homeomorphism in W11 can be approximated strongly W11 by diffeomorphisms, okay? But clearly, strong topology W11 implies both area strict and strict, okay? So these two closures clearly coincide. And then during my PhD with Aldo, we proved that actually any homeomorphism in BV can be approximated strictly and area strictly by diffeomorphisms. By diffeomorphism in BV, but clearly diffeomorphisms in BV are also in W11 because they are regular. Okay, so in the end, what you are really interested in the planar case is looking for the closure, in some sense characterizing the classes obtained by the closure of the homeomorphisms in BV, either in the strict or the area strict sense. okay, about the problem in general of looking for closures of homeomorphisms, then let's say the situation in the plane in the Sobolev setting is kind of well understood. The first results dates back to Ivanets and Janioninen. For P bigger or equal than the dimension, they prove that the strong and weak closure of diffeomorphisms with respect to the weak strong, I mean with respect to the corresponding Sobolev norm, are the same. And the limit class contains mappings which are all continuous and enjoy the inf condition, the monotonicity. While then more recently, Guido de Philippis and Aldo Pratelli, they pushed not actually this argument, with a different argument. They were able to prove that still weak and strong closure coincide, but this time when P goes below the dimension, so P bigger or equal than 1, but this time you can have discontinuities in this limit class, and but discontinuities are have a specific shape. They are cavitations, okay, finitely many cavitations, and they can cook up a property that is characterizing this limit class, which is called this non-crossing condition, which I'm not explaining it now because I will explain it better later with some pictures. And what we did was to consider the closures in BV. Okay, so try to finish with the planar setting. Okay, Sobolev setting was okay. Let's do the BV one. So the first result we have is in common with Daniel and Aapo and Standa. We started studying some properties of strict limits of homeomorphisms with bounded variations in the plane, and we showed that actually this is a good class because the limits well behave with respect to the non-interpenetration of the material. I will be more precise on this in a second. And we also show that, okay, we have more complicated discontinuities, not just cavitations, but we have also fractures. And fractures is something that experimentally you engineers see, okay, in the as limits of deformation. So this is not strange, okay? And then in another series of more recent works with Daniel and Aapo, we characterize these classes. We characterize the strict limits of homeomorphisms and also the area strict limits. And we prove that they are the same, that the limit class is the same, and we find a suitable generalization of the non-crossing condition that was introduced in the Philippis Pratelli, that we call non-crossing BV condition, that would take care also of the bad discontinuities that we have now, so the fractures, because they didn't have the fractures. Okay, in this slide I'm cheating a bit because we don't prove exactly this, but we prove this. I mentioned before the strict topology. Actually, what we do is something that is even a stronger result because it's with respect to a weaker topology. That is the Manhattan norm. So you know the Manhattan norm of a two-component vector is the sum of the modulus of the two component. Okay, so here we have, let's say the derivative of the deformation is a matrix. So you have to intend this as the total variation of the derivative in the horizontal direction and the total variation of the derivative in the vertical direction. Okay, and we ask for strict convergence with respect to this norm. Okay, so what we actually prove with Daniel and Aapo is that the characterization of the closure with respect to the Manhattan strict is the NCBV condition, okay? So what, okay, before telling you what is this NCBV condition, let me tell you some nice properties of strict limits of the homomorphisms. Strict, not Manhattan strict, I will tell you later. Strict limits. Clearly, okay, since we can have fractures, like the standard concept of topological image that was already mentioned by someone, I'm sorry, I don't remember who, introduced by Muller and Spector, this doesn't apply to our case now, okay? So we have to kind of generalize this concept, and our idea was to use the approximating sequence. So we define a proper multifunction that we call F tilde, that to each point of the pre-image associates in the image all the possible limits that you can obtain using the subsequences of your originating sequence, okay? And then actually you can prove something nice. You can prove these two characterizations of this image set, these, let's say, geometric characterizations. And thanks to them, then we can prove very nice things. So the first one is that this definition is independent on the approximation sequence, otherwise it won't be a good definition. Second, that the topological image of a point is good, so it's closed, non-empty, and connected for every point. It's a singleton for almost every point, as you can expect. Okay, this is straightforward. The function is differentiable almost everywhere. Also, since our approximating sequence is a sequence of homeomorphisms, it immediately gives also the sequence of the inverse mappings. What we can prove is that the sequence of inverse mappings is weakly star convergent still to some BV map, and the multifunction associated to this BV map is actually what you expect. So it's the inverse, in some sense, of the multifunction that you obtain as a limit of the FK. Oh, and then here comes the nice thing about the non-interpenetrability, that is the image of two disjoint sets can at most collapse. So the image of disjoint things is essentially disjoint. So it means that they collapse on each other on something on smaller dimension, okay, but they cannot overlap. And especially not on positive, not doing positive measure, okay? So this is something that works good for elasticity. So summarizing, we have these nice things that I already, the first two I already discussed them. The third is that we also have a notion of distributional Jacobian for, let's say, the limit map as the limit of the distributional Jacobians of the approximations. And this limit distributional Jacobian is doing exactly what you would expect to do. So in a cavity, it's measuring the area of the cavity that is open in the image. And in a fracture point, it's measuring the length of the jump, okay? And again, I said it many times already, that we have cavitation and fractures. And the good thing is that we can bound the length and the opening of the fractures via the total variation of the singular part of the gradient. So this is something that you would also expect. All we said for BV strict limits is true, actually also for the Manhattan strict limits. I don't enter into the detail why, but basically you can expect this. Basically, if you are BV, the restriction of your function is BV on almost every line. So you can work on the lines, vertical and horizontal slices, and being BV there means, and strictly converging there means that you are actually just Manhattan strictly converging. So all the properties passes also to this weaker, in this weaker sense. So what is the NC condition instead? The non-crossing condition from Aldo and Guido, it's much easier if you look at the pictures instead of reading the definition. So remember that they have to deal with mappings which can have cavitations, but cavitations are not many, actually just not even countably many, there are finitely many. So they can, the definition of NC is that they can, for any grid, so imagine that you have a mapping that goes from the unit square to the unit square being the identity on the boundary, and you take any grid that is not touching cavity points, okay? Then this would be, for example, the image of this grid. So if your map is NC, it means that you can always injectify the image of the grid, being as close as you want in the uniform sense to the original image of the grid. Okay, so you can always find injectifications which are close in the uniform norm as much as you want. Okay, so non-crossing, I think already Dan said this, implies monotonicity is a stronger condition. Then with Aldo and Daniel, we actually tried to come up with a more handy equivalent reformulation of the non-crossing condition. We failed, but we thought, okay, maybe we can ask that the map is just non-crossing on lines, not on grids. And if you just ask your function to be non-crossing on lines, so without having real crosses, then actually this is not enough to imply the non-crossing on grids. You have to require on top that your Jacobian is positive almost everywhere, then, which is something that is very reasonable in linear elasticity, so there it's still okay. But in general, it's not true. Non-crossing condition on lines doesn't even imply monotonicity, so that's epic fail, I would say. Then what is the non-crossing BV condition? Then a little point, it will be on grids, not on lines, because on lines doesn't work. It's just let's say, the definition comes somehow, uses somehow the non-crossing condition already introduced by them, but adapted to this less regular setting, because we have the fracture points, so we cannot, since fracture discontinuities, they have H1 measure strictly positive. We are in a plane, so in general, Hn minus 1 measure strictly positive. You cannot ask your grid to avoid fracture points. You will have jumps on the grid, for sure. So you have to deal with these jumps somehow. You can ask only, but there is one thing that you can ask, so that the crossing of your grids are not on the jump points. This we want, okay? But this we can ask. And then, thanks to the multifunction that I defined before, we can associate an image to the grid we have, okay? So we will have some continuous curve, continuous deformed grid in the target configuration. And we basically, what we do is we parameterize this continuous deformed grid in the target space with some mappings that is keeping as much information possible from the original F, okay? And then we ask that this G is satisfying the non-crossing condition. All of it, we call it non-crossing BV condition. So once again, with pictures that is helping, we have a grid that is touching fracture lines. So the image of this grid would have jumps, okay, in where you have the fracture points. With the multifunction, we have a field. We fill these jumps with the segment that is connecting the endpoints, and then we parameterize these curves with some G that is actually equal to F on the crosses of the grid, and then on the segments in between, it's just a parameterization at constant speed, for example. Okay, and then we ask that this G is non-crossing, so that you can always injectify it, being as close as you wish to the original image. Okay, what we prove with Daniel and Aapo. The first result we had is this characterization of the Manhattan strict limits. So the NCBV condition is the properties that characterizes the class where you have Manhattan strict limits of homeomorphisms. So whenever you have a sequence of homomorphisms in BV, being the identity on the boundary from the unit square to the unit square, if this sequence is Manhattan strictly converging, so satisfying this, then the limit map is NCBV. On the other way around, if you take a BV map that is NCBV, then you can construct a sequence of homomorphisms which is converging like this, okay? I would like to talk about this result, but there is no time at all. So I go on with the newest result, that is the NCBV property characterizes the area strict limit of homomorphisms. Okay, so the statement is basically the same. Whenever you have a sequence which is area strictly converging, then the limit is NCBV. Whenever you have an NCBV map, actually you can do a much finer construction and construct a sequence of homomorphisms which is converging area strictly. Okay, so the construction here is much more precise than the one in the Manhattan strict characterization. Okay, if you believe this result about the Manhattan strict limits, so I hope you believe me and take it for granted, then the implication that area strict limit implies NCBV is immediate, no? Because area strict implies Manhattan and Manhattan implies NCBV, okay? The point is the other way around. How, from an NCBV map, how you can construct the approximating sequence in area strict approximating sequence? Well, you have to use two very fine properties of BV mappings. which are the rank one property of Alberti, the celebrated Alberti's theorem, that is telling you that all the singular in the polar decomposition of your of the gradient of your NCBV map, sorry, BV map in general, then actually the matrix is rank 1. So it's going, the deformation is going in one specific direction at any singular point. And then there is this Federer-Volpert result that is telling you, okay, also the function is doing exactly this. So it's jumping in that direction between the traces that you see. Okay, so the combination of these two facts with a lot of work, much work that Dan did, allows us to isolate, if you, sorry, I didn't say this, but we are still in the nice setting where we have a mapping that goes from the unit square to the unit square being the identity on the boundary. So, okay, then inside your unit square, you can isolate an open set S, and S stays for singular, where basically all the singular part of the gradient is concentrated. It means that outside S, the singular part of the gradient of the NCBV map is very small. So, while on S, it's basically almost all concentrated there. But on S, the absolutely continuous part of the gradient is small. Since S is very small, as a small measure, it's easy to achieve this. Okay, and then basically what you do, you cover S with the union of this joint, essentially these joint squares, which satisfy a sort, not a sort, a Lebesgue point type estimate for the total variation of the singular part of the gradient. So on these squares covering S, you don't have basically, or you have very few absolutely continuous part of the gradient. And let's say the singular part there is behaving most likely just in one direction on this square. This square is so tiny, you can imagine that at the center of the square, this is not true what I'm saying, I'm cheating, but it's just to give you the idea. If at the center of the square, maybe the rank 1 property is telling you that the gradient there is going in one direction, then in a tiny square around this point, all the singular part of the gradient wants to do the same, okay? And this is crucial. We call sigma the union of these like squares covering S. So S is included in this sigma. And then what you can say, outside this set where all the singular stuff points and singular part of the gradient is there, outside you are almost a W11 map, okay? And so the NCBV condition is actually almost NC, okay? So you can construct the approximating sequence using exactly the result of the Philippis and Pratelli. Not exactly, but like the ideas all come from their paper, okay? And you can do it strongly in L1 because they do it strongly in W11. So the derivatives are converging strongly to the absolutely continuous part there in L1. The point is what you do on sigma instead. Okay, on sigma, okay, we have NC. I lost the. Sorry. Okay. We are starting from an NCBV map. Okay, so don't forget this. We know that we can always injectify, in some sense, the images of the grids. Okay, so let's assume that the grid is constructed in such a way that the boundary of these squares QR that I used to construct the sigma covering S are part of the grid. And then we injectify. And you can always injectify with piecewise linear curves. So you can imagine that to each QR of your sigma, you can associate a polygon now in the image, in the target domain, okay? And then what you want to do is provide an extension in these squares, which will be then in the polygon, in the interior of the polygon in the image. How do we do it? With it's called a minimal extension. Let me tell you first the result that I obtained with Aldo a few years ago. That is not the one we are using here, then I will tell you what we do here. But this one is easier to understand. So let's say here you have your square QR, and through the injectification, we have this is how the boundary is mapped onto the boundary of the polygon. This is a piecewise linear homeomorphism here. Then, okay, we have just the boundary that we know where it goes. We want to fill with something. We want to do an homeomorphic extension theorem that will be something piecewise affine. The idea was already explained a little bit by Alexis, but we do it differently here. So we know, because we know GK, we know who are the images of these two yellow points, the end points of the horizontal slice. For example, one is here and one is here, okay? So since we want an homeomorphic extension, clearly, whatever extension we do, it has to connect the two images, right? Okay. And since we are counting for, let's say, either if you want the W11 norm or the total variation, anyway, those two norms count for the length of the curve that you do in the image, okay? So the best thing that you can do in the image to shorten, to keep this value as low as possible is to do the geodesic, connecting them, right? You can do this for every horizontal slice and for every vertical slice, okay? You sum up, you kind of integrate, sorry, not sum up, all the length of the geodesics that you construct in the image space, you come up with a number, okay? You do it both for the horizontal slices and the vertical slices, you come up with a number, okay? This number, for sure, clearly is just a number, so it's not an extension, not a bound, but for sure is a lower bound for the Manhattan norm of your homomorphic extension, the Manhattan in the horizontal and vertical direction, okay? If one would extend using exactly the geodesics, clearly then you won't get an homomorphism because you lose injectivity immediately. But with Aldo, we proved that we are always able to construct a homomorphism that for which you are not doing the geodesic, but almost, and you keep the injectivity, the one-to-one property. So you are almost optimal in the Manhattan sense with respect to the Manhattan norm. This was with the horizontal and vertical direction, okay? With Daniel and Aapo, we extended this result. Instead of starting from square, we can actually start from quadrilaterals, and we can do the almost optimal extension with respect to any rotated Manhattan norm, okay? And this is what we do here, exactly in the direction given by the rank 1 property for the singular points. So in a bed square, we have, okay, clearly the total variation of your extension is smaller than the Manhattan, rotated Manhattan norm of the same extension on the square. But now this extension is done in such a way that this Manhattan norm is almost optimal. Okay, so this is for sure smaller than what was the Manhattan norm at the beginning, okay, plus a small error. But now, since we are in a singular point, like around a singular point, so in one of the singular squares, we know that basically the absolutely continuous part of the derivative is very small in both the directions. The singular part of the derivative is very, very small in this direction because it's almost all of it going in the eta direction, okay, thanks to the rank 1 property. So in the end, you can, this is smaller or equal than 1 plus some epsilon that then will go to 0 times the singular part of the derivative, okay? And okay, this is clearly smaller than the original total variation. And now this is crucial that we are doing the almost optimal thing because now we can recover the strict convergence by the lower semi-continuity of the total variation. So you can sum up over all the squares in this sigma, and by the lower semi-continuity of the total variation, you have that the total variation of the NCBV map is smaller than this lim-inf of this guy, which is smaller than the lim-sup, but the lim-sup is smaller than this guy without the epsilon, so just this one. So they are all equality. You have actually a limit, and this gives you the strict convergence on the bed set, okay? And I am a bit over time. I'm very, very sorry. So I don't talk about open problems. I just thank you for your attention. Thanks.